Hello, in this video we are going to go over the solution of the problem 124, binary tree maximum pass sum. Imagine that I have a tree like this one, and one possible solution could be this, 1 plus 2 is 3. The other solution could be the summation of these three nodes, is 13, and actually the solution is this pass, that is summation of these nodes. And the important point is that this path doesn't have to pass through the root, and the value is 22. And if you consider the left value and right value of the node 6, on the left side I have 9, on the right side I have 7. So the 9 that I'm calculating here is summation of the 4 and 5. So that is this pass that I got 9, and this pass I got 7. And if I just use this formula, value of node value left and right plus left and right value, so I get 22nd. So that is because I got from the left side, I got from the right side, and I have a value of the node itself. So the summation is 22nd. So I can do this for all of the nodes of the tree, and that is actually the trick to solve this problem, because the node 6 in this path is, in a hierarchical manner, is the highest node in this path. So between 4, 5, and 7 and 6 is the highest in our tree. So the idea is to calculate this for each node from the left side and right side. And the reason we are doing that is that it is much easier to calculate value for children of a node than calculating, for example, value of one child and the parent. So that would be much more difficult. So saying that, we are going to calculate exact same thing for all of the nodes of the tree. So for the leaf nodes, it's just easy. We return 0 for left and right. And now let's look at the node 1. For node 1, what value should I return? So that is 1, because that's the value of the node. For the next one, for the node 3, I should return the value 3. For node 5, 5, 7, 7. Now let's look at the node 4. So for node 4, I have left is 3, right is 5, and the value of the node is 4. And we saw already that we need to return 9 here. So what we do is to find the maximum between 3 and 5 and plus that to the value of the node. So we are technically following this formula. So we say, what is the value of the maximum of the left and right, which is 5, plus 4 is 9, we return 9. Now let's do that for the node 6. So the maximum between 9 and 7 is 9, plus 6 is 15, and for the root node or node 2, between 1 and 50, the maximum is 15, plus 2 is 17. So in this way, we can calculate all of these values. And in the same loop that we are doing that, we can, because we have left and right value and the node value, we can calculate the values at the same time. So for all of the nodes, I can calculate the values. And between these values, what I care is the maximum. So in the same loop, I can keep the maximum just by comparing to the previous calculations. So that would be the solution to this problem. Now let's go over the code. So the code is that I'm showing here. First I have the class that defines the node. It has left, right value, and also I define the exact same tree here. So the solution that we have, we need one thing to be calculated, and that is the maximum sum, this value. So I have a function here, max pass sum, that returns this value. And initially we set this value as a maximum, as a minus infinity, very, very low number. And then we calculate what would be the higher number than this. So then I have a function, maximum gain, and the input to that function is the root of the tree that I'm providing to that. So now inside this recursion function that I have. So first of all, this maximum sum should be non-local, and also whenever we get to the where we don't have a node, so for the leaf nodes and the value on the left and right side, as we talked about that. So for those things, we return 0. And for each node, we can for the left side and the right side, we put them as input to the function again in a recursion manner, and we calculate left and right. And after that, we calculate that current value, which is the node value, left and right, and then that current sum that we have, we compare that to the maximum sum so far collected. For the first iteration, it was minus infinity, and then it changes. So we get that max and update our max sum. And the value that we return is the node value plus maximum of the left and right. So technically, this return is this green triangle, which is the maximum of left and right plus node value. And this current sum is that orange square that we had. So node value left plus right. Now, if we run that, so I can run it again. So this is the solution. Now let's go over the picture to see what we calculate. So for the node 1, first of all, this is a recursion, so it's gonna start from the leaf nodes. So for the node value 1, so this one, you can see we have the current sum that we have. This one is 1. So the maximum value, which is updated, is 1. And the return value, this one is 1. And you can see the left and right values are 0. So then for node 3, so you see left, right is 0. And the current sum is 0. For 5 is same. For 7 is same. And then when we go for the for example, node value 4 here. So you can see I have left is 3, right is 5, and the current sum, this one is 12, and the maximum sum is 12, and the value I return is 9. Now let's go to the, so I got 12 here actually, and then for node 7, so you can see that the current sum was 7, but the maximum sum is 12 because already we had the maximum 12 here, so it's not still higher than 12, so that would not be updated. And then for example, when we get to node 6, so we can see our current sum is 22, which is 22, which is our desired value, and we update the maximum sum. And when we get to root, so our current sum is 18, but our maximum calculated is 22, and we are not going to update that. So our maximum sum returns 22. So, and that is the value that we return at the end. So that's the solution. So let's look at the time and space complexity. So for the time, so we are going to go, so for the time, it is because we are going to visit each node. So it's gonna be n. So or the big O is n. But for the space complexity, so for that one, it depends on your tree. If your tree is very unbalanced, so all of the nodes involved are in, I mean, on one side, not distributed evenly. So that would be big O of n, but in the best case scenario is log of n. So unfortunately, it is mentioned wrong in the LeedCode solution. But if you go to the comments, people discuss that and you can see that for the space complexity, so best case scenario is log of n, and worst case scenario is n, and your value should be between these two numbers, but we usually consider the worst case scenario, that is what we should return. So the space complexity is actually of the order of n. So that's the solution to the problem 124. This is considered as a hard problem. So there is a simple version of that. That is the depth of a binary tree. That is problem 104 that we have another video for that. I recommend you to also watch that video, and I think that would be better to start with that one first and then working on this one. Thank you so much for watching this video.